So I want to continue on our discussion with recurrence relations, mentioning some of the terminology that we'll need. This first one deals with the order of a recurrence relation, and that should have been in bold. A recurrence relation of order k is an equation that expresses the nth term, an, in terms of the k previous terms of the sequence. So it steps back 5 to get a value. So here's one that's order 5. An is an minus 1 squared, so it goes back one term, minus 3 an minus 2, so it goes back to the two terms, plus square root of this mess here, an minus 5 plus n squared. So it goes back 5 terms. Now it doesn't have all 5 previous terms there, but it does have to look back to 5 terms to calculate the value of an. And this right here tells me that it's order 5 because it goes that far back. We'll call it linear if the recurrence relation has this form right here. This is still order k now, where it is it involves the previous k terms, and the way they're combined involves two operations: multiplication by coefficients, which may include n in some way, or n minus 1, etc., but not terms of the sequence, aj, in the coefficients themselves, right? So these are coefficients that do not involve the terms of the sequence. And then the other thing that is involved in the combination is additions. Okay? So the only way the terms are combined is by multiplication by some coefficient and then addition of the terms. Now there may also be another portion to it, this guy right here, that only depends on n but not the terms in the sequence. That's possible as well. So other terms are homogeneous, which means in the above the fn term is 0. There is no additional portion, no additional term besides the ones that involve the sequence. And a constant coefficient means that the coefficients, the c's above, c1, c2, ck, are constant, no n dependence. They're just truly constants. So that's constant coefficient. We're going to put these things together and refer to a recurrence relation as, just by an abbreviation, as L for linear, homogeneous with an H, constant coefficient. So linear, homogeneous, constant coefficient. Okay, so that's a special category that's easy to work with, the easiest to work with. So, if we look back at some of the ones we had before, we had early on an is equal to an minus 1, and that fails to be LHCC in one area. What would it be? Doesn't have constant coefficient, not constant coefficient. And then another we had earlier was an is equal to an minus 1 squared plus 2. This is not LHCC by what? By what property? What fails? Well, I mean, it looks linear, and in fact it is linear. It looks like all the coefficients are constants. Did I say it was linear? Well, that's the thing that's wrong. Look right there. It isn't just the terms multiplied by coefficients that depend on n, but not the terms of the sequence itself. So this is a nonlinear piece, like so. Now the classification is useful. It's not a huge thing, but I'll probably give you some examples where you can analyze whether they fit these This one, by the way, is not homogeneous, also not homogeneous because of the extra term there that doesn't involve a term in the sequence, it's just added on there. So those are some of the terminology. Some of the terminology we'll use, and maybe another example. Let's see, we had one that's not linear, not constant coefficient, not homogeneous. Yeah, let's just do a basic one that does meet those categories. So an is equal to 3an minus 1 plus 5an minus 4, like so, would be linear. It is indeed homogeneous because there's nothing over here extra but the terms. And it has constant coefficients, and its order is 4, right? Order 4. So that's kind of examples that we'll work with. One of the next ones we're going to work with, because we've already dealt with the first order linear, is the second order linear, homogeneous, constant coefficient recurrence relation. And so second order here, and it's linear, so we just have some coefficient an minus 1 plus some coefficient an minus 2. That's the only way they're combined. And there's no term over here. That's a 0, so that's the homogeneous part. The C's are constant. C1, C2 constant. That's the constant coefficient part. Yeah. So we're going to look at those kinds of things there. And I guess what we're going to try to do is figure out, okay, what kind of solutions might we have for this? Playing off of the order 1, 1, and I'll just scribble this down over to this side over here. For the order 1, 1, when we had an is ban minus 1, the solution, the general solution, was of the form an is equal to some constant b to the n, like so. So some power function, it turns out to be a power function, that was a solution. Okay? That's a constant. And it could have been anything. But that constant turned out to be the same as the 0th term, right? Okay. But that could have been anything to start off with. We could start our sequence with anything. So, the sequence an is equal to, let's see if I can scroll down a little bit here and say an is equal to, 4 an minus 1, like so. We could start it with anything here for a0. What do you want to start it with? Well, I can't hear anybody talking. I better do it, right? So I'm going to just kind of randomly pick a number there. Let's take 11. Okay? We can start it with 11, and the next one is 44, right? And the next one is 4 times that, which is what? 176. 4 times 44 is 176, and on and on and on. But this could have been anything. So yeah, this is going to be an is equal to c 4 to the n, right? Where the c is equal to a0. Right, so it doesn't work quite exactly that way for the second order one, but there are similarities enough that we're going to be able to make some headway with this. And so in the next little video clip, we're going to deal with this a little more clearly and develop exactly how that's going to work out.